Hey. All right, so this is kind of a condensed version of our acid and bases properties or introductions lecture. um, and acids and bases are all around you at home. Um, whether you're eating them, drinking them, using them to take a shower in the morning, wash your clothes, clean your house. Everything's an acid or a base, basically, except for the water that you're drinking. Let's hope that that's something that's neutral. When we take a look at acids, the common taste that you're going to see there is, something's going to be sour. Okay, anytime we have an acid. Whereas if you're tasting something that's basic, it's going to have more of a bitter taste. So you can think in terms of lemons. If I put a lemon in my mouth, I'm going to say it tastes sour. Lemons are extremely acidic. If I get my mouth washed out with soap, soap is something basic. Any type of soap is going to be bitter tasting, which then takes us to the feel. When you think of soaps, whether it's dish soap, a bar of soap, laundry detergent soap, if you were to put it on your fingers, it's going to feel slippery. Okay, whereas if you put an acid on your fingers, most times it's going to burn it. And I shouldn't say most times because Coca-Cola, the soft drink, is extremely acidic, but yet if you get it on your skin, it's not going to burn it. In the lab, we used some of that paper where we would dip it, our stir stick into our liquid, and then we would put it on the litmus paper, it's called. And it would either turn red or blue. And that's what you see with acids and bases. Anytime you put something acidic on litmus paper, it's going to turn it red, whereas basic stuff is going to turn it blue. Okay, so the next thing we start talking about is conjugate acids, conjugate bases, and then they pair up. Here's going to be Lemoyne's general rule. Anytime you have an acid, it's going to give up a hydrogen. Oh, I'm so sick of the telemarketers and politics stuff calling our house. So as soon as you can label your acid and your base, then it's really easy to see the conjugate acid and the conjugate base. When we take a look right down here, this is the base and this is the acid. How did they know that? Well, you kind of have to compare it to the product side. So water here is considered an acid because it's going to lose or give up one of these hydrogens. And the reason I see that is when I look over at the product side, I see OH. Okay, one of those H's was taken away. Well, where did it go? It was put onto NH3 because on this side it became NH4. So real easy. You take a look at I'm going to erase that if I can figure out how to do it. Remy's next to me snoring, and actually she's awake. She's snorting while she licks her paw. Okay, so who's the acid? H2O. Why? Because it lost an H. So I label that my acid. And whatever one's the acid, that means the other one is the base. Now, if it's the acid on the reactant side, that means it's going to be the conjugate base on the product side. And whatever was the base on the reactant side becomes the conjugate acid on the product side. Now, when we look at these problems, water I just labeled as an acid, whereas in the next one, it's a base. And how can it be both an acid or a base? We call that amphoteric, meaning that it can go, oh my gosh, either be an acid and lose a proton or an H, or it can gain an H or a proton and be that base, okay? Don't worry too much about the hydronium and hydroxide. Down on the bottom, some formulas of common industrial acids that you would see. Nitric acid, we just take our nitrate, and put an H in front of it. That's the formula for nitric. Sulfuric acid would be H2SO4, and these are inside your chem helper, and hydrochloric acid would be HCl. Okay, what's indicating that all of these are acids? They have an H out front. And we've said that earlier in the year when you guys named them or wrote the formulas for them. Anytime there's an H out front, it's an acid.